Okay, so last time I taught Cal 1, we didn't cover section 4.2, and now we are, so I don't have notes for it. So I'm going to have to record a video to go over some of those. But I have the notes for 4.3, so we're going to move into this. 4.2 is different, so we don't have to cover it in that order. So what we're looking at in section 4.3 is maxima and minima. So we're going to figure out how can we determine where a graph has a max or a min. So when we look at this parabola, does it have a max or a min? Yep, a min. It's got a low point. So here we have fancy definitions. So f of x has an absolute maximum at x equals c if f of c is greater than or equal to f of x for all x. So the c value, like x equals c is an x value. F of c is the y value. So if the y value is bigger than all the other y values, then it's a maximum. Likewise for the minimum, if the y value is smaller than all of the other y values, it's a minimum. Now, a little point here at the bottom about the way questions are phrased. So we're going to see some things where they say the extremum is blank, or what is the extremum, versus the extremum is at blank, where or when is the extremum. So when it says the extremum is, this is asking for the y value. Like when we say, what is the absolute max? That's asking, what is the highest y value? When it says where or when the extremum is at, this is asking for the x value. Most of the time, though, when we're focusing on absolute max and min, we're focusing on the y value. Like, what is the absolute highest value or what is the absolute lowest value? All right, so this is asking find the absolute extrema. So absolute max. What's the highest this graph gets? Yep, infinity. So when the highest we get is infinity, then there is no absolute max. So none or does not exist. Now, what about our absolute min? So our point on the graph for the min is at 1 comma -1. So we would say the absolute min is -1 at x equals 1. Like that's one of the ways I'll phrase it. But when it asked for the absolute extrema, all it's really asking for is the y value. I just like to correlate the data for this is the absolute minimum and it occurs at this x value. All right, now we've got a graph that doesn't extend to infinity. And we've got some endpoints. So let's start with absolute max. So what is the absolute highest this graph gets? Yep, 12. And that is at x equals 4. Then the absolute min is at -4, or sorry, is -4 at the x value of 2. The 2 is a little more questionable. But that looks like roughly the middle there. All right, so this graph does continue on to infinity on either side. Like our domain is all real numbers here. But looking at our graph, our absolute max, highest the graph gets, somewhere around here, is 5. And then our absolute min is -5. Now, picking out the x value they occur at, like it's somewhere between 3 and 4, somewhere between -3 and -4. But a lot of the homework questions don't always ask for the x value, they'll just ask for the y values. If they do ask for the x value, then it should be like on an integer. So what questions do y'all have so far about pulling this off of the graph? All right. Slightly different graph then. We've got a straight line, we've got a closed circle and an open circle. So an absolute max has to be a value that the graph is actually at, that is a filled in point. So the absolute max here does not exist. Because any number I say could be the absolute max, there's always another x value that will have an even higher y value. Because we never actually hit 5, so we're always just getting closer and closer and closer to it. Now, absolute min, though, that's at -1. Well, the value is -1 and it's at x equals -1. So questions on this one, because it is a little bit weirder having the do not exist, even though it looks like there's a point there. All right, so this crazy graph is doing a whole lot of wonky stuff. So when I look at finding my absolute max, like my overall highest point is occurring there, and my overall lowest point is down here. So when I look at those 2 points, like what's interesting about those points from a calculus perspective? Say it again. So there's like two relative high points and two relative low points. So all of those like highs and lows are doing something interesting with the derivative. Yep, the slope at those points is 0. So if you look like as we start, I think of it like a roller coaster. So we're going up, 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 and then like there's a point where we're no longer going up and we're about to go down. The slope at that point is 0 because we're going from a positive slope to a negative slope. So our absolute max and min, the slope at those points is 0. But like we noted, those aren't the only points that have a slope of 0. There's two other points in there that also do that same behavior. But if we're going to, using an equation, figure out these points, I can take an equation, take the derivative, set the derivative equal to 0 to figure out where the slope is 0. And then that'll give me all the x values. So then I'll have to do a little more figuring to figure out what the absolute max and min are. All right, so let's look at this little setup. This is a very deliberately picked weird graph. So what are the x values where the derivative equals 0? All right. Yep, so I've got one at 0 and I've got one at 1. But when we look at this graph, where are the local extremums? So where is the absolute max occurring? Yep. And then our min is whatever the endpoints are. Ah, okay, hold on. I answered the wrong question. So where is the absolute max occurring at x equals 2? So local extrema are points that just really close to them, they're the high or the low. So they may not be the high for the overall graph, but just when we look real close to it, that's the high value. So where is the derivative equal to 0 and where are the local extrema? Those are the same. But when we talk about the absolute max and min, we have more considerations. You're right, x equals 2 is also a local extrema. So the derivative equals 0 gave us some of the local extrema value, but not all of them. So that's what the last question is getting at. So setting the derivative equal to 0 will get us most of the local extrema, but it may miss some. The other spot, the absolute max, which is also a local max, the derivative there is undefined because the left side and the right side it's making a sharp corner point. So when we're looking for local extreme values, we want to look at where is the derivative equal to 0, but we also need to look at where is the derivative undefined. So when we're looking at an equation and we take the derivative, that's what we're going to look for. So local extremum occur where the derivative is 0 or where the derivative does not exist. Points that satisfy one of these two conditions are called critical points. So a lot of the work we're going to do, we're going to take the derivative, set it equal to 0, solve for the x values. All right, so looking at this graph, identifying all the critical points is where the slope is 0 or where the slope is undefined. So I've got one at 5, one somewhere between -4 and -3. I got a corner point at 2, another corner point at -1. Oh, sorry, that's -5. Looks like about -3.4, -2, and -1. Now, looking at the graph, though, where's the absolute max? Yep. And our absolute min was at 2. So where else should we look when we're trying to find an absolute max and absolute min besides the critical values? So like what's special about those points where the absolute max and absolute min occurred? Or what do we call those locations? So we call those the endpoints. So when we're looking at a graph that has like a fixed interval, then we're also going to plug in those x values for where our domain is restricted to when we're looking for an absolute max and an absolute min. Now, if we're only looking for local maximum and minimums, well, I mean, usually when we ask for local max and mins, we're not restricting the domain. We're just asking in general, where do critical points occur? But like endpoints can sort of fit the definition for a local max or a local min. It's just usually the definition says there has to be like values on either side. So the endpoints are sort of don't fit the definition. But anytime we're talking absolute max or min, we have to check the endpoints as well. Now, when we're looking at a graph, it's kind of like, duh, that's the high value, that's the low value. But when we're not looking at a graph and we just get the equation and the domain, we're going to be solving for all this algebraically. So this is an extra step we need to remember. So when you're finding absolute max or mins without graphing, you have to check the endpoints and you have to check the critical points. So you find critical points by taking the derivative and setting it equal to 0 and setting and checking where the derivative does not exist. Now there is a nice little note here. Make sure the critical values are within your endpoints. So sometimes the endpoints they give us are going to exclude some of the critical points we would get. So if our domain is like from 1 to 3, and one of our critical points was at x equals 0, x equals 0 isn't on our domain restriction, so it's just not a consideration for an answer. It's a potential local max or min, but it's not within the interval. Now, to tell what the absolute maximum value or absolute minimum value is, you have to plug in all of your x values into the original function and see what the y values are. And that's why it says original function in all caps, because we're so used to working with the derivative that it's really easy to like default go back to the derivative. But if you start getting a bunch of zeros, you plugged it into the wrong thing. And then we compare to figure out where what the biggest y value is and where that occurs, what the smallest y value is and where that occurs. All right, so now we're going to try it out. So find the absolute maximum and minimum values of the function f of x equals x to the fourth times e to the negative x on the interval -2 to 9. All right. So when I'm working an absolute max or min problem, I like to keep a running list of the x values I need to check. And I write it in a t-table because I'm going to have to figure out the y values for each one. So this just kind of gives me a running list to work from. So I have to check my endpoints. Now we're going to find other critical values. So we're going to take our function and we're going to take the derivative of it. So x to the fourth times e to the negative x, this is a product rule. So derivative of x to the fourth is 4x to the third times keep e to the negative x the same, plus, now I keep the x to the fourth times the derivative of e to the negative x. So that'll be e to the negative x again, because the derivative of e to the something is e to the something, times the derivative of something. The derivative of negative x is -1. The derivative of first one kept the second one the same, kept the first one, derivative of second one with chain rule, yes. So now I actually have to work with this function. I'm going to have to I'm setting it equal to 0. So I'm going to clean it up a little bit. All right, now when I go to set this equal to 0, there's some stuff that's the same in both of these two things that are being subtracted. So I'm going to factor out the common stuff. So I've got an x to the third and an e to the negative x in both of those terms. And now I'm going to write my leftovers. So that leaves me with just a 4 minus an x. So if I remultiply 4x to the third e to the negative x, yep, minus, then it'd be x to the fourth e to the negative x. Now, whenever I have a product that's equal to 0, each thing in the product has the potential to be 0. So I have x to the third can equal 0, e to the negative x can equal 0, and 4 minus x can equal 0. So x to the third equals 0 gives me x equals 0. That's the only number to the third power that's equal to 0. E to the negative x, this is an exponential graph. It's a decreasing exponential graph. But exponential graphs have a horizontal asymptote of 0. So e to the negative x never hits 0. So we get no critical values from that term, and that's okay. The graph is also never undefined, so that'd be our other potential consideration there. So yeah, no critical values from that. And then this, I add the x to the other side, so I get another critical value of 4. So I'm going to put 0 and 4 on my list, and those are between my end values. So there are my 4 critical values that I'm going to check. So I'm going to take each of these x values and plug it into the function. So that'll be f of -2 is -2 to the fourth times e to the -2. Now, since I've got to compare these numbers, I want the decimals. Now, if I type that in, though, the calculator is going to give me decimals. So -2 to the fourth power times e to the negative negative 2 is just 2. So we get 118 point stuff. Okay, so now we do 9 to the 4th times e to the negative 9. And that e to the negative 9 makes this a decimal. So 0 to the 4th is 0. E to the negative 0 is 1. 0 times 1 is still 0. And then f of 4, 4 to the 4th times e to the negative 4th. All right, so what is the biggest this graph gets on the interval? Yep, the 118. So there's our absolute max. And then our absolute min, our lowest value, is at 0. And then there's the picture of the graph. So negative 2 is off the screen, but we can see the 0, there's the min. 4 has a local max. And then 9 is just our endpoint, a little bit less than 1. So questions on how that one played out? All right, so this one, the phrasing is a little bit different. Find the critical points of the function on the interior, it should say of its domain. So that means the first thing we have to figure out is the domain of this function. So when we're finding domain, my colleague Chris writes this with smiley faces, but there's 3 domain restrictions. So if I am ever dividing by something, one of my domain restrictions is that the something can't equal 0. If I'm square rooting something, the something has to be greater than or equal to 0. And if I'm taking the log of something, the something has to be strictly greater than 0. So the domain for this graph, the 2x squared doesn't have any domain restrictions, but the natural log of 3x does. I can't take the natural log or the regular log of a negative number or 0. Log itself has a restricted domain of only positive numbers. So my domain is 3x is greater than 0. And I divide the 3 out and I get x is greater than 0. So on the interior of its domain, that means x equals 0 is not a critical point because the function doesn't actually exist at x equals 0. But we're looking for what are all the critical points where x is a positive number. So to solve for that, we're going to take the derivative, set it equal to 0. So my function f of x equals 2x squared times the natural log of 3x. So we got a product rule there. So derivative of 2x squared will be 2 times 2x, so 4x to the first, times keep natural log of 3x the same, plus, now I keep 2x squared the same, and now I do times the derivative of natural log of 3x. So derivative of natural log of something is 1 over something times the derivative of something. The derivative of 3x is just 3. So we've got 4x times the natural log of 3x plus 2x. So now I'm going to set this equal to 0. I'm going to factor out common factors. So both of the terms have a 2x. So that leaves me with 2 times the natural log of 3x plus 1 as a placeholder. So I've got 2 things being multiplied that are equal to 0. So 2x equals 0 is one of the things. 2 natural log 3x plus 1 is the other thing. So 2x equals 0 gives us x equals 0, but we're not using 0 because we are only looking for positive numbers. So that one we just ignore. Now our 2 natural log of 3x plus 1 equals 0. So I minus the 1 and divide by 2. So I have the natural log of 3x equals negative 1/2. Now we need to get rid of natural log. So what undoes a natural log? Yep. So e as a base. So I'm going to say e to the left side and e to the right side. So the e to the natural log of something just gives us the something. And then this is e to the negative 1/2. And then we divide by 3. So x equals 1/3 e to the negative 1/2. Now that is a positive number, but you can type it in just to be sure. So the critical point, the only critical point we get is that weird number. So even though it looks like x equals 0 was a critical point, 0 is outside the domain. So that is not part of our answer. Our answer is only that weird number. All right, so our next one, we're back to finding absolute max and min, but we have a fixed interval. And our function is a weird, not quite a polynomial, but polynomial-ish. The x to the 2/3 is going to be kind of weird. So off to the side, anytime I'm doing absolute max and min, I write down my 2 endpoints to make sure I remember to test those as possible maxes and mins. Now we're going to take the function. So f of x equals x squared minus 3 times x to the 2/3, and we're going to take the derivative of this. So the derivative of x squared is 2x minus 3 times the derivative of x to the 2/3. We can still use our power rule. So we'll have 2/3 x to the negative 1/3. 2/3 minus 1 is negative 1/3. And then this is what we're setting equal to 0. All right, so I'm going to clean this up a little bit. So that's 2x minus 2 x to the negative 1/3. Let's consider our algebra a little more carefully. So x to the negative 1/3 is the same as dividing by x to the positive 1/3. So I'm going to combine these two terms. So this gives me 2x to the 4/3 minus 2 all over x to the 1/3. And let me rewrite that because that is god awful written. 4/3. So when we have a fraction equal to 0, when we're solving for critical values, we can split this into set the top equal to 0 and set the bottom equal to 0. So x to the 1/3 equals 0. I raise both sides to the third power. And I get x equals 0 as a critical value. So I'm going to put 0 over on my chart. Now the 2 times x to the 4/3 minus 2. I'll add the 2 and divide by 2, so I have x to the 4/3 equals 1. And then to get rid of the 4/3 power, I have to use the 3/4 power. But luckily the other side is 1, so 1 to a power is just 1. So now we have 4 values that we have to check and find y values for to figure out what the absolute max and min of this function are. But before we do that, questions on how we found all the critical values here, because it is definitely a weird looking thing. All right, so now we're just plugging in these 4 values into the function. So f of negative 1/2 is negative 1/2 squared minus 3 times negative 1/2 to the 2/3. Now, when you're typing fractional powers, make sure to put parentheses around the fractional power as well. And some of your calculators, if you type the fraction button as an exponent, it may not like that syntax, so you may have to type it as 2 divided by 3. But negative 1/2 squared minus 3 times negative 1/2, nope, not squared, raised to the 2 divided by 3. My calculator doesn't like the 2 divided by 3, so I'm going to have to square it. and then raise that result to the 1/3 power. All right, the rest of them should be easier to type in. So not 0. Skipping ahead, sorry. So 2 squared minus 3 times 2 to the 2/3. Two squared minus 3 times 2 raised to the 2 divided by 3. Negative 0.76. Yeah. 0.7622 negative. So 0 squared is 0, minus 3 times 0 to the 2/3, also 0. So we get a lovely 0 value there. So 1 squared is 1, minus 3 times 1 to the 2/3. So 1 minus 3 is negative 2. All right, so what's our max? Yep. And what's our min? Yep. So the highest y value is 0. So our absolute max occurs at 0, 0. And then our absolute min is a y value of negative 2, and that occurs at x equals 1. X squared minus 3 times x to the 2 over 3. Oops. So there's the graph of our function. So we can see at negative 1, 0, and 1, I should have gotten negative 1 in my work, and I didn't. Hmm. Either way, when we make our domain restrictions from the negative 1/2 to 2, we can see that 0 and 1 value. That's our max and our min when we make those cuts there. Mm, okay. Here's where I missed the plus or minus. So when we did the fourth root, bleh, the fourth root needs a plus or minus the same way a square root needs a plus or minus. Now, the -1 was outside our domain restriction, so it wouldn't have been a critical value, but that's where I was missing it in the algebra. But this is why it's not bad practice when you're working a problem, like to look at the graph and see where you can see critical values. Now, sometimes those critical values are not going to be the pretty integers we see here, but we can definitely see there was an extra value that our algebra didn't show us. So that's why I went looking for where my mistake was. And it was a very subtle mistake. This is a very easy mistake to make. So good mistake to make in class. Well, it's 1 to the 3/4. So here, yeah, let me write it here. So we had x to the 4/3 equals 1. So I'm going to do this as 2 steps instead. So I'm going to get rid of the third part, the 4/3, by raising it to the third power. So x to a power, we multiply the powers. So 4/3 times 3 leaves us with x to the 4th. And then 1 to the third power is still 1. So raising both sides to an integer power, like whether it's positive or negative, like the integer power will just take care of that. It's when we're getting rid of integer powers that we have to be more careful. So undoing the fourth power, getting rid of the fourth power, like one way to write that is to write that as the 1/4 power. But the other way to write that is to write it as the fourth root of both sides. And any even index root works like a square root. So whenever we do a square root, we have to remember the plus or minus. So we have to do the same thing for a fourth root, a sixth root, an eighth root, any even index root is going to have that plus or minus that we have to recall in there. But when I did it as a fractional power, like I forgot that fourth root was an even index root because I wasn't writing a root. So my brain overlooked that. Now, we usually don't make radicals quite that bizarre on the test for questions like this, but it's not a bad practice problem. All right. I want to take a moment and look at the homework for 4.2, what I didn't get to do like lecture notes on. So I'm going to flip the share to web work because the first question is interactive and weird looking. So the two big ideas brought up in section 4.2 is linear approximations and differentials. So a differential is the dy and the dx notation that we were using. A linear approximation is the change between two y values. So when I'm looking at a random point on a function, if I find the derivative at that point, I can find the slope, and then I can, for that particular point, write the equation of the tangent line. We call that tangent line a linear approximation of the graph close to that value. So sometimes functions are like really hairy looking, or plugging into the original function requires a lot of extra math. But if I only really care about values really, really close to one particular x value, and the graph near that x value is not doing super crazy changes, then I can come up with the equation of the tangent line, and that gives me a pretty good approximation of the graph. And using a line is a lot easier than using whatever the disgusting original function is. But using this line has some error involved. So I can click and drag this point. So we see for some values, like the change between the actual function value versus the line's value, like can be pretty big, depending on how far away from my x value I go. So my delta x has a slider up here, and this is changing. Like if I look really far away from the point where my line is tangent, then my error approximation is pretty big. But if I didn't need to look that far from my x value, maybe I only needed to look like 0.3 from my x value, then my error is only 0.12. That's still kind of a big error, so maybe I'd want to shrink my delta x down even more. So when I'm looking at whatever this weird x value is, like 0.15 maybe, I can only look 0.17 away from that value to keep my error down to 0.05. Now, if I move my x value further away, like here, the graph is almost getting close to a line. Like there's not a lot of change when we're further away from a weird critical value. So here, like even having a delta x of 1, my approximation error is only 0.07. If I keep that delta x smaller, my approximation error gets really tiny. So when we're not around critical values, the linear approximation is actually a pretty good estimate for the graph, as long as we're not moving too far from our tangent point. Now, what this question asks us to do is a little bit weirder. So part 1, suppose that we fix the value delta x to be 0.5. So I'm going to move my slider so it's 0.5. Now, what is the smallest positive x value for which the error in the approximation will be less than or equal to 0.5. So now it's asking us to drag the point until we hit an approximation error of 0.5, 0.05. And this appears to be at 0.6. Now, you can zoom the this in some. But yeah, 0.6 seems to be where it's at. Now it says, suppose we center the linear approximation at x equals 0.5. So we're going to move the red point there. Now it's on 0.5. And then what is the largest positive value of delta x for which the error in the approximation will be less than 0.01? So now it's wanting me to slide my delta x until my error value gets real tiny. So it looks like 0.23. It doesn't like my 0.6. All right, so let's fix this back on 0.5 and zoom in. Maybe we'll try this 0.5 too. Sure. Might even take 0.5 here, although it probably shouldn't. Yeah. So first question on the web work here, very weird, but it gives you a really nice visualization of the linear approximation versus the actual curve and seeing that difference between the y values. Now, all the next problems are straight up asking, find the linear approximation to the function y equals f of x near x equals a. All right, so I'm going to screenshot this. Flip my share back to the OneNote and work this out real quick. So a linear approximation is just a really fancy way of saying find the equation of the tangent line. So to find an equation of the line, I need the point and I need the slope. All I have right now is an a value, but that is my x value. So at x equals -2, I need to know the y value, the function value. So f of -2 is going to be -2 plus -2 to the fourth, and that is 14. So I have the ordered pair -2, 14. That's the point where my equation is occurring. Now I need to know the slope. So slope, we're going to take the derivative of the function. This is a nice little polynomial, so I'll have 1 plus 4x to the third. And then I want to know the slope of the tangent line at x equals -2. So that means I'm plugging in -2. 1 plus 4 times -2 to the third. That's -8 times 4, -32 plus 1, -31. So our equation of the tangent line, y minus y1 equals m times x minus x1. So y minus 14 equals -31 times x minus -2. And then since it says L of x equals, I need to actually solve for y. So -31x, this will become plus +2, so that'll be -62, and then we'll add 14. So that is what they want for L of x. That's the linearization at x equals -2. So I'm going to type in -31x minus 48. And it is happy with that answer. So that'll get you through the good chunk of the homework. And then towards the end, it starts asking for differentials, which is just a really fancy way of saying find the derivative. But I can run through an example of that next class.